to infinity.
-2 to 3.
Good. -2 to 3. Don't forget about that piece. Union, and then where do we go?
3 to infinity.
3 to infinity. So that's how we find out where this function's continuous on. All right. Any questions on that one?
Sort of. So you're saying so negative infinity to -2, because we technically have to separate it as well since we're trying.
Good. Because here's negative infinity.
Uh-huh.
Here's infinity. And then here's -2.
Mhm.
And here's 3. Now do you see the intervals?
Okay, yeah.
There's negative infinity to -2.
Yeah.
There's
Yeah.
-2 to 3. And there's 3 to infinity.
Okay.
Make more sense?
Yeah, it is better when you do it like that.
It's a good visual.
Yes.
All right. Okay. And then the next one, f of x equals the cube root of x squared minus 4. What type of function are we dealing with?
The odd positive integer.
Well, 3 is an odd positive integer, but more, I'm looking for the name of a function, and we're just going to say that this is an odd radical. And what do we know about odd radicals? What is the domain of any odd root?
Negative infinity to infinity.
That's it. That was easy. Then this means the next one must be what type of radical?
Even in. Oh, wait, no.
Yeah.
Okay.
This is a even radical because what type of root is that?
Even.
Well, it's an even root,
Square
but it's the square root.
Square root, yeah.
There you go. Okay. And before we find out where it's continuous, let's go ahead and find this function's domain because we have a little bit of work to do. So remember, with even roots, we have to take whatever's inside the house and set it what?
Equal to 0.
Greater than or equal to 0. Right there. And now we're going to solve for x. So here, if we solve for x, we're just going to get x is greater than or equal to 2. All good?
Yes.
And now, in interval notation, we are going to say that this function is continuous on what interval? Where do we start?
2.
2. Is it included?
Yes.
And we head towards?
Net infinity.
The right.
Infinity. The right. Towards infinity. And there you go. That's a little lesson on domain and continuity. If you know a domain of the function, well, first, if you know the function you're dealing with, then you find the domain of that function. You can then state where that function's continuous on. Any questions on that page? All right. Next. Oh, this is a fun one. So this next example is going to get us used to making sign charts. You're not going to see sign charts till the, what is it, second exam, I believe, or maybe the third exam. But as long as you see how to make a sign chart now, it'll help you out for in the future. So we're going to use Sine Property. So it says if f is continuous on some open interval AB and f of x doesn't equal 0 for all values of x in this open interval AB, then either the y values f of x are greater than 0 for all x in this open interval, or all your y values are less than 0 for all values of x in this open interval. So basically, again, I like to translate everything to English. What we're going to do is we're going to make a sign chart. And the x values we found, we're going to plot those on the sign chart, and we're going to pick test numbers. And what these test numbers are going to tell us is where our y values are above the x-axis or below the x-axis. That's all we're going to do. Sounds like a lot, but it's not. And then when you break up a number line, this is actually called a partition number. So the next definition says a real number x is a partition number for a function f if f is discontinuous at x or f of x equals 0. So we are going to solve this function given for x, and whatever number we plot on the number line is going to be considered a partition number. Later on, they're going to be considered critical numbers, but that's not for a while, guys. For now, they're just partition numbers. Okay, so solve this inequality by creating or constructing a sign chart and express the solution in inequality notation and interval notation. So here we go. All right, first up, we are given this rational function, x plus 1 over x minus 2. So whenever I'm given a rational function, the first thing I want to do, I'll call this step A, is solve for its domain. So what is the domain of this rational function going to be?
X equals 2.
Good, because you're going to set the denominator equal to 0 and solve for x. But can it actually be equal to 2?
No.
No, because the denominator will become what number?
0.
0. Good. And then B, the next thing we're going to do is solve for the X intercept. The next thing we're going to do is solve for the X intercept. So to make this really, really simple, to find the X intercept, you just take the numerator and set it equal to 0. So domain comes from the denominator. X intercepts come from the numerator. Can't put it any easier than that.
I'm going to write that down real quick.
Yeah, I'll say it one more time. Domain comes from the denominator. X intercepts come from the numerator. And what is my X intercept here?
-1.
X equals -1. I guess I'll box that one too. And this now kind of makes sense for being partition numbers, because if you read the definition of a partition number, it's only considered a partition number if the function is discontinuous at that number, which means our function is discontinuous at 2, or if your function equals 0 at that number. Well, if I plug in -1, the whole function is going to become 0. So these fit the criteria for my partition number. Okay. Just wanted to show that. And then next, step C, we create our sign chart or number line, whatever we want to call it. I'll say sign chart to be more accurate. And here we are. Here's my sign chart. Here's negative infinity. Here's positive infinity. And what two numbers am I plotting on it?
-1 and
-1. And -1 is going to be a closed circle, and +2 is going to be a what?
open circle because it's
Open.
undefined, right?
There you go. Good. And now what we're going to do is list the intervals you see off of this sign chart. So I'm going to say intervals, and my first interval is from -infinity to -1. And my next interval,
Oh, yeah.
-1 to 2. And my last interval,
2 to infinity.
2 to infinity. Good. And then what we're going to do next is pick test numbers in between each interval.
Would the 2 be in a bracket though? Or no?
That is a good question. And since I'm only stating intervals on this number line, I'm not stating a domain. We don't have to put proper notation. So it would only get proper notation if I was stating an actual domain. So for now, it can stick with the parentheses.
For test points, can we plug in 1, +1?
One moment, let me get there. Test points. And if you wanted to put a bracket on that -1, I wouldn't be mad at it. But If my math lab is telling you to put in intervals like that, then you're going to have to put the parentheses on it or it'll count it wrong. Because once again, there's a difference between stating intervals and domain. These intervals have nothing to do with our domain as of right now.
Yeah, it is pretty picky.
Yeah,
Yeah.
it can be. And if it is, just always, when you turn in your work or if you get stuck, email me. I can go in there and be like, all right, look at your work, look at the problem, say if you typed it in wrong, and I can give you credit back for it.
Thank you.
Yep. Okay, so we have 3 intervals, which means we're going to have 3 test points. So let's pick a number from this first interval, negative infinity to negative 1. What do you want to pick? What was that?
-2.
Good. And then my next interval, negative 1 to 2. What do you want to pick?
+1.
Positive 1. How about I make it easier and we say 0?
There you go.
1 will work though. There's nothing wrong with picking 1. And then the last interval from 2 to infinity, what are we going to pick?
3.
3. 300. Perfect. 300 to work as well, as long as it's in the interval. Okay. So what we're going to do now is take all of these test numbers and plug them into that function above. So you're like, oh man, we got to do this one by one, right? But I have a little trick for you. If you have, I'll just pull up Desmos. Why not? Just to make the number crunching a lot faster. There we go. Get that, move this, do that, go here. And right, let me type in the function first. So I'm on Desmos, and I'm going to type in the function just like I see it. X plus 1 over X minus 2. And then I hit this little gear icon up here, and I click this XY chart. And now, look at this. I'm going to go calculate my test numbers and type in exactly what I wrote over here. If I -2, look, it's already there. -2, I get 0.25. 0, it's already there. I get -0.5. And 3, it's not there, so I'll just type it in on one of these. Let me see. I'll type in 3, and I get +4. Look at that. Number crunching's done super fast. All right.
But you could also get that just by doing the simple math, correct?
Yeah, you can just do that
Okay,
by
good.
plugging the numbers in. Why not? Why not? I'm just trying to save you some time, right? But if you
Okay.
like doing that one by one, go ahead. I don't have much time for this class, only an hour and 15, so I got to keep moving, right? All right. So let's go back to this sign chart. I'm going to go back to this screen. And now, like I said, all we want to know is where are my y values above the x-axis and below the x-axis. So the way we read that is we say, when we plugged in a number from the first interval, we got a positive output. So this means that no matter what number you pick from this first interval, the y value is always going to be what?
Positive.
Positive, which means we are going to be above the x-axis. And then we say, when we pick the test number from the second interval, the y value is negative. This means that no matter what number we pick from -1 to 2, your y value is always going to be
Below the x-axis.
below the x-axis, negative, right? And then from 2 to infinity, no matter what number we pick, the output will always be above the x-axis, positive. Look at that. And now we have all this information to answer one simple question. It was the question asked in the very beginning of this problem. It wants to know where this function is greater than 0. So basically, what this inequality is asking, what this part here is asking, it says, on what intervals are we above the x-axis? On what intervals are we above the x-axis? So D, I'm going to rewrite it. I'm just going to say R of x greater than 0, R of x representing my rational function. So all this wants is what we said, inequality notation and interval notation. So first, let's go with the interval notation. Looking at the sign chart above, where are we on what intervals are we above the x-axis? What do you see?
Negative infinity to -1.
Negative infinity, -1, and where
And then
else?
2 to
Last one.
infinity.
2 to infinity. And now here is where you could put a bracket on the -1, but you're not going to, because what does this inequality say?
Greater than.
You would only put a bracket if it said greater than or
Equal to.
equal to.
That's what I was gonna ask right now too.
Good, good. All right, so these are the intervals where we are above the x-axis. So this is considered your interval notation. And I'm not sure if it's going to take the union. It might just take a comma to separate them. But
Ugh.
I guess when you get to that part of my math lab, I'm trying to remember all the problems from last semester. Okay, but now this wanted to put it into inequality notation. So basically what we're going to put is, no, yeah, this is going to be easy. So basically what this set says is that every number has to be less than -1. So how would you, I guess I just said it, right? To put this into inequality notation, you would say x is less than -1. Does that make sense?
Yes, sir.
And then how would I put this one into inequality notation?
X is greater than 2.
That's it.
Yeah.
And that's your
Yeah.
inequalities.
Okay, that's it.
There you go. All right, guys, that was fun, right? You're like, oh yeah, the domain and X Intercept were easy. And then you come across the
Could we
C.
go back and re-watch this lecture
Yeah,
later on?
I recorded it. I kind of recorded it too late though, like I did
Is it
last
one
time.
like
I keep
last
messing
year?
up this class. So I recorded on this page. I missed this one, but
Okay, because
but
I'm gonna go
on
back and watch it later, maybe tomorrow.
yeah, but they're like I said, like all of these lectures have been recorded already. So you can actually go watch this whole lecture already, not the one I do today. But if you want to watch the one that we do today, then I'll have that up as well.
Is it on your YouTube channel?
It's on my YouTube and everything's in the modules, remember? So if you go to 9.3 module on our Canvas, you're going to see a video that's there that covers all these notes already.
Perfect.
Yeah. So since I like to record these late, I'm just recording these new ones because maybe it's nice and fresh and not outdated, even though I finished all my recordings for this class during the summer and half of the first semester, half of the fall semester, something like that.
Okay.
Yeah. But yeah,
Thanks.
so like if you ever missed a day, the video's there. You be like, hey, I'm going to miss today. I'll watch the video, you know?
Nice.
Stuff like that. Yeah. Okay. Last one, example 4. Let's do this. Let's get this Thursday over with. All right. Example 4, graph the function f, locate all points of discontinuity, and discuss the behavior of f at these points. Okay, so here we are given a piecewise function again. We saw a piecewise function on Tuesday. So this wants us to graph the piecewise function. And one of the easiest ways to do that is to make XY charts and pick points based on the restrictions given. So let's run through this really fast. So for A, let's go ahead and graph the first function, x squared. But if we're going to graph x squared, we can only pick values that are less than what number?
1.
1. So here we're going to graph x squared. So I'm going to make an XY chart. I'm going to have x equals and y squared. I'm going to put the restriction right above it. So what we're going to do, even though it says we have to be less than 1, I'm going to start at 1. And now give me numbers less than 1.
0.
0.
0.
-1, -2.
-3. That's all that's going to fit on our graph. Now go ahead and plug all these numbers into x squared. Fair enough. You'll get 1, 0, 1, 4, 9. Everybody good with that?
Yeah.
Guess I should write my ones the same over here, right? There you go. Okay, but before we move on to the next one, I just want you to take note that can we actually use this point?
Negative, because it can't be greater
We
than
can't be equal to 1. It only says we have to be
less than.
less than 1. But there's a reason why I use this point, and you'll see when we graph it. So just know for now that this point will be
Undefined.
undefined. Undefined. So let's actually go ahead and graph this one already before we graph the next one. So I'm going to plot the point 1, 1, which since it's undefined, it's going to be what type of circle?
Open.
There we go. There's 1, 1. And then everything else is closed. 0, 0,
You
1,
said,
1. Go
I'm
ahead.
sorry.
Go ahead.
Yeah.
You said the 1, 1 was going to be undefined? You said?
Yes.
Okay, because it's,
Because the reason it's undefined is because what does my inequality say?
x is less than 1.
And therefore, does it actually mean that we can, does it mean that a point will exist?
Yeah,
It would only be a defined point if it said x was what?
Equal to.
Equal to, less than or equal to. If it was that, then we would fill the point in.
okay.
Make sense?
Yeah, thank you.
Okay. So that function's graphed. Let's go ahead and graph the other one. We have x and y equals 2x. And this is for values of x greater than 1. So once again, it's telling me we have to be greater than 1, but I need a starting place. So I'm going to choose 1 and just give me numbers bigger than 1. That will fit on my graph.
2.
2.375.
There you go. Oh, 7. Did you say 375? 50, 11 times. Good. All right. Plug them in. 2, 4, 6, 8, 10. But once again, we run into this situation. Can we use 1?
No.
Nope.
Nope. It'll be undefined. Again, because of the inequality. All right. So that means when I graph 1, 2, it's going to be another what type of circle?
Open.
Open. Don't sound so excited, okay? 1, 2, 3, 4, and then everything else will be closed circle. Let's go up to, up to, up to, right? So this is what we look like. There it is. We've graphed the function. All right. So one of the easiest ways to graph a piecewise function is to make XY charts for each piece of the function and follow its restrictions. All right. And include the number it's telling you you can't be, because that makes it a starting point for you. If you forgot it, if you don't graph it, you're going to miss out on some information. Okay. B says locate all points of discontinuity. So I just want to ask you to look at this graph, and where do you think this function would be discontinuous at? At what x value?
At 1.
At 1. So
We only give the x value then, huh?
That's it. You only give the x value.
Okay.
Yeah. But if we did want points, I don't think it will. You could state the points, but I wouldn't. I'm sorry. Go ahead.
I'm so sorry. So discontinuity, because they're both on the same, that's why it's 1, right?
Exactly. Well, and let's say that we had a more complicated problem. Let's say there was an open circle up here too. Then we would state that as well as being discontinuous. Okay, so we know that it's going to be discontinuous at 1. And then C says, find any y values at the point of discontinuity. Well,
1 and 2.
Can we actually state any y values at the point of discontinuity?
Would it be 1 and 2 or no?
Would
Well,
it be
they're both
1.5?
They're both open circles. So can we actually state a point, a y value existing there?
-1.
No, we can't because they're open circles, huh?
Exactly. Since they're both open circles, no y values exist. Do you guys see that?
And if they were closed?
If they were closed, you would state both of them.
Okay, got you.
So
Wait,
for
wait.
the
Go ahead.
we're choosing, and so let's say for like for B, we're choosing 1 because it's an open circle, or because of
Exactly.
its location. Like
Both.
like how you were saying, where if you had an open circle, like in a random other spot, because it's an open circle, that's also why you're choosing
That's
that?
why we're choosing it, right?
Okay.
Like, let's say if these both were filled, then we wouldn't have nothing going on and we would be done with this problem.
Okay. And
So
in all cases, would it be an X equals something to answer that question?
exactly. Yeah.
Okay.
So now when we get to the y values, well, we can say that when x equals 1, the y values are undefined.
Oh, I thought we're gonna put does not exist.
Remember, we have to think about our terminology here. Limits don't exist now, and points are undefined.
Okay.
Got it? So we got to change it up a bit now. Points are undefined. Limits don't exist. And once again, we can't state y values because they're both open circle. Does that make sense?
Yes.
Okay.
Because they're both open circle, that's why it's undefined. If they were closed, then it would be.
Exactly. Then we could say, if they were closed circles, then we could say y is 1 and y is 2.
Okay.
Okay.
There you go. There you go.
All right, now I understand.
We're getting there. We're getting there. Okay.
Okay, very
then-
quick question. Like,
Yeah.
let's say for that, the one where X is greater than 1.
Uh-huh.
Okay, let's say if that one was a closed circle.
hmm
So then it would be X equals to 1, right?
Exactly. It would
But-
still be, yes.
But if that other one was located, I guess, on the 2 and it was still an open circle, we wouldn't write it down because it would still be an open circle. Unless if it was closed is when we do write it down.
Yes. Yes.
Okay,
So,
I got you now.
you got it. Yeah. So if that was a closed one, you would write 1 or
Right.
either or, right?
Right.
You
But
got it.
since
You got
they're
it.
both open, there is no Y.
There is no y
Okay.
value there.
All right.
Good. Good. All right. And then D says, find the limit as x approaches C of f of x, where C is the point at which f of x is discontinuous. So basically, in a nutshell, we are going to examine this function at the discontinuous x value of 1. So all I'm going to write here is the limit as x approaches 1 from both sides of our piece function f of x. And now look at your graph to answer this limit question. As I approach 1 from the left, what y value are we getting close to?
1.
1. And then as I approach 1 from the right, what y value are we getting close to?
2.
2. So what does that tell you?
the limit.
There is no
go
limit.
to the left.
There is no limit because once again, what is the limit from the left?
1 on the right is 2.
Good. The limit
they're
from the
not
left
even.
is 1. The limit from the right is 2. Therefore, the left hand and right hand do not equal because 1 does not equal 2, which means that at the very bottom, this means that if the left hand doesn't equal the right hand, the limit does not
Exist.
exist. Woo! My goodness. Excellent. And that's it, guys. That is continuity. And I think example 4 and example 3, they look exactly like some of your homework problems. So that's why I have them on the notes for you.
Okay. Okay, that's what you have homework for.